Okay, we're going to attack 3b here. It's the same exact scenario. We've got this right triangle, so forget A. Pretend it's not there. Okay, we're going to answer B. A right triangle is changing, and its height is increasing at 1 inch per second. Again, that's dh dt. We know that. That's how fast the height is changing. It's positive because it's increasing. The base is increasing at 3 inches per second. That's the rate of change of the base. That's dB dt equals 3 inches per second. And although I cross this out like a big ding dong, we don't need to answer this question, but we need to know that at this point in time, the height is 4 and the base is 9. Okay, so we have a right triangle before we even get to the question, where we know the base is changing and the height is changing. So look, even though I know the base is 9 at this point in time, I'm not going to put a 9 down here. Because once I do that, it locks the base in at 9. And the base isn't always 9, it's just 9 currently, but it's changing. So because it's changing, we can't put a 9 there. We have to put a variable for it, which I'm going to put as the base. And this is going to be the height. So I know how fast each one of those things is changing, and I know what they happen to be at this point in time. Again, 4 and 9 are not special. I just made those numbers up. I could have easily picked like 10 and 15. All right? But we want to know how fast is the angle between the hypotenuse and the base changing. Well, the hypotenuse is over here. So this is that angle. So I want to know how fast that angle is changing. I'm looking for d theta dt. That's what I really want to know. That is my special little thing I'm trying to find. I'd be so happy if we could find this. So in order to find a rate of change, you've got to come up with an equation that links it to some other rates of change that you know. Since I know how fast the height is changing and I know how fast the base is changing, I'm going to use a trig function that links this angle to the height and the base. And because that's the opposite side over the adjacent side, that's what we have, I'm going to use tangent. So I'm going to use the fact that tangent of theta has to be whatever the height is divided by whatever the base is. Okay, and again, I can find theta right now if I plugged in 4 for h and 9 for the base, and I can do tan inverse and find out what theta was, but that doesn't matter. I just want to know how fast it's changing. So that means we can't use this equation we have. Like we're going to use it, but that's we're not done. We need something else from it because we don't want theta. We want d theta dt, which means we need to derive this equation to get d theta dt to pop up. And a common thing for students to do when they derive this, you get secant squared theta, right? Most people know that that's the rule for tangent, hopefully. But then they forget to multiply by the derivative of the inside thing. And the derivative of theta is d theta dt. And that's the chain rule. I'm going to give myself some more room over here. That's the derivative of the left side. The derivative of the right side, because it's a quotient, and these are all things you got to look out for. Anytime you do any derivative, you got to look out for a product, for a quotient, for a chain. So this is a quotient, so we're going to do quotient rule. And the quotient rule says you're going to multiply the denominator by the derivative of the numerator, that's dh dt. Oh, then you're going to subtract that by the numerator times the derivative of the denominator, and that's all over the denominator squared. So I'll be honest, that looks like a mess, right? There's all kinds of stuff happening in that equation. Our goal, though, and this is what you got to keep in mind, is for us to find d theta dt. We want to know that, and we happen to know base, dh dt, height, and dB dt, and we know the base that's down here too. It's the same base. So now that I've derived it, I can plug all that stuff in, and that's just going to simplify down. So this left-hand side is still secant squared theta, which we're going to take care of in a second. D theta over dt. And then we're going to plug in all this stuff. The base was, what, 9? And the rate of change of height was 1. Minus the height is 4. And the rate of change of the base is 3. Divided by, that's me, again, just plugging in all this stuff right there. Divided by the base squared, and the base was 9. So this is going to be divided by 81. So we get 9 times, or 9 minus 12, let's write this out here. That's 12, right? 9 minus 12 is negative 3 over 81. And negative 3 over 81 reduces to negative 1 over 27. And that equals the right or the left-hand side, okay? So right here should be secant squared theta. But if we're going to find d theta dt, I need to know what secant of theta is. Again, at the point in time in question, which is when the base is 4 and the height is 9. So this is when you go back and start looking at all your information, trying to figure other things out. I'm going to use the fact that I know the base and the height because I'm looking for theta, which isn't a rate of change. It's like a measurement. So I'm going to use the other measurements I know, 4 and 9, to find the measurement I need, theta, okay? Particularly secant of theta. So I'm going to draw this triangle again, and the height is 4 and the base is 9 currently. And by Pythagorean theorem, that's right? Height is 4, base is 9. Pythagorean theorem, which is a squared plus b squared, that's going to be 16 plus 81, which is going to be 97 square root. Okay? Making sure I did everything correctly here. I don't want to mess this up and then, okay, I feel like this is good. Okay. So, we got that going on, and we have theta, which is right here. Okay? I want to know what is secant squared of theta. Well, just from this triangle, you could find theta if you had a calculator, but I have no idea what theta is, and we don't need theta. We need secant of theta. So we're going to skip the whole fact that we need theta, because we can just find secant theta without it. I know that cosine of theta in this triangle is 9 over root 97. So secant of theta must be root 97 over 9. That's the reciprocal of cosine. So I'm going to take that and use it to drop in here to what secant squared is. But because it's secant squared, not secant, I actually have to square it out. So if secant is root 97 over 9, then secant squared is 97 over 81. Okay, and that boils this whole equation down to really simple here. We have d theta dt. It's multiplied by 97 over 81, so we want to solve for that. So we are going to take this, negative 1 over 27, and multiply it by the reciprocal, which is that. And to reduce that down, 27 and 81 can cancel out a 9, right? So this is going to become, oh no, we cancel out 27. 27 goes into 81 3 times. So 27 becomes a 1, 81 becomes a 3 when you cancel those out. So you're left with negative 3 over 97. And the units on that, again, you can keep track of units the whole way through, but because we're talking about theta, and for calculus to work the way we want it to, we're always measuring that in radians. And since it's a rate of change, this is radians per a unit of time, which in this case we were using seconds in the whole question.